Hello, and welcome to a Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 2.4, Cooling and Heating Phenomena. In Chapter 2.4, we look at two more applications of first-order linear differential equations. We will start with cooling and heating problems, and then move on to mixing problems. Other applications that could follow after this chapter are multiple compartment problems. Now I'm going to be breaking up the lecture videos for Chapter 2.4 into multiple videos covering Newton's law of cooling and the mixing problems separately. I may even break them up further to give you different types of examples of each. It'll make it easier for you to navigate to specific types of videos. Let's start with the cooling and heating problems. Consider a pizza that's heated to 450 degrees Fahrenheit. That is taken out of the oven and placed in a room that's 72 degrees Fahrenheit. We naturally expect the pizza to cool down as time passes. Suppose that we actually realize that we can't eat the pizza right away because it's just too hot, and we decide to wait until the pizza cools to 110 degrees. How long will we have to wait? To answer this question, we must apply Newton's law of cooling. Now recall from chapter 1.1 that Newton's law of cooling says the rate of change of the temperature of an object, T, is proportional to the difference in the ambient temperature, M, and the temperature of the object, T. We would like to write Newton's law of cooling as a differential equation. So recall, Newton's law of cooling says, when we translate this into an equation, the rate of change of the temperature, this gives us the derivative. The rate of change of the temperature is dT dt is equals proportional to, we'll have our proportionality constant K. Recall this is also referred to as our thermoconductivity constant. And is a measure of how well an object maintains its temperature. It's proportional to the difference in the ambient temperature and the object's temperature, which our author has written as M minus T, where the thermoconductivity constant K is greater than 0. Now you may notice that in some of the resource videos that are presented in Canvas in Chapter 2.4, so not in these guided lecture videos, but in the reference videos on the homework page, that there is an alternate form for writing your differential equation. In the alternate form, the videos represent the Newton's law of cooling as dt equals K times T minus M, where they've changed the order of the terms in the parentheses. But they've also made K be less than 0. Now I'd like you to identify that this form is equivalent to the form I've given you, though. It's equivalent to our author's form. Because if you imagine that K, your thermal conductivity constant, is negative, you could distribute just the negative sign into the parentheses. Only the negative sign. If you distribute the negative sign, the T becomes negative, and then the M becomes positive, which matches, I think I said that backwards. The T becomes negative, and the M becomes positive, which matches the form given by our author. Now, I'm going to be using the first form of this differential equation, that is the one that our author provided. Qualitatively, we expect the temperature of an object to approach the same temperature as its surroundings. To confirm this, let's identify the equilibrium temperature of the differential equation. Okay, so remember the equilibrium is found when your derivative dt is equal to 0. Now, since your differential equation is K times M minus T, we want to find when this is equal to 0. Now recall, K, our thermal conductivity constant, is always greater than 0. So that the only way this differential equation is going to equal 0 is if your second factor is equal to 0. Also recall that M is your room temperature. That's a constant. So the only way that this is going to equal 0 is if the temperature of your object, T, equals M. If your pizza is the same as the room temperature, you imagine its temperature won't change over time. A pizza is not going to start to boil while sitting on the counter. So if you're imagining our equilibrium solution, T equals M would be about here on your graph. Now imagine what the differential equation look like if T, the temperature of your object, is greater than M. If T is greater than M, then your derivative T prime is going to look like K times, now if T is larger than M, then M minus T is going to be negative. If T is larger than M, then M minus T is negative. So that if K is a positive number and this is negative, then your derivative will be less than 0. This tells us that if we have an object that has an initial temperature T naught that's greater than M, the object will cool down over time and approach your room temperature. Similarly, if T is less than M, if the temperature of your object is less than the room temperature, then T prime is going to look like K, your proportionality constant. Now, if T is less than M, then M minus T is less than M. M minus T is going to be a positive number, and K is a positive number, so that the sign of your derivative is greater than 0. This tells us that if an object's initial temperature T naught is less than the room temperature, it will heat up over time as it approaches room temperature. Because solutions that are above T equals M approaches M, and temperatures that are less than M approaches T equals M. This tells us that our equilibrium solution, T equals M, is a stable equilibrium solution. Okay, let's look at some examples. Consider the pizza problem that we did earlier. The pizza is heated to 450 degrees Fahrenheit. It is taken out of an oven and placed in a room that is 72 degrees Fahrenheit. After 1 minute, it's already cooled down to 370 degrees. And the question we would like to answer is, how long will we have to wait for the pizza to cool to 110 degrees? Let's start by writing our initial value problem, our IVP. Newton's law of cooling says that the rate of change of the temperature, T prime, is proportional to the difference in the ambient temperature and the room temperature. Here, the ambient temperature, M, is 72 degrees, minus the temperature of the object, T. We also know that our temperature at time 0 is 450 degrees Fahrenheit. And we know that after 1 minute, the pizza is cooled to 370. So T of 1 is 370 degrees. Now, there are multiple ways to find solutions to this differential equation. In your homework, I think you explore 3 or 4 different methods you could use to solve this. I'm not going to use every possible method, but I do want to provide some variety. So in this video, I'm going to show you how to solve this differential equation using the integrating factor method. However, in the next example, I'm going to use a different method. I'm going to use the non-homogeneous principle. You can use either method for any problem. I just need to be able to show you that there are multiple methods that you could use. So for this example, I'm going to find the solution by the integrating factor method. To apply the integrating factor method, I would like to rewrite this differential equation in the standard form for a first-order linear differential equation by distributing your constant k and then getting all the variable t on the left-hand side. Now, if we distribute k, we'll have t prime is equal to 72k minus kt. And then write the kt on the left-hand side. In this form, we can now identify what our integrating factor is going to look like. So remember, our integrating factor, mu, is always going to be e to the integral of p of t, where in this example, p of t is going to be the term or the factor in front of t. Here, the term or the factor in front of t is just k. So we'll be looking at the integral of k dt. Now, since k is a constant, this will be e to the kt. Now, recall with our integrating factor, we want to multiply both sides of our differential equation by the integrating factor. Now, if I follow the method or the steps I used in our previous example videos, we distributed the integrating factor into the parentheses on the left-hand side and wrote our differential equation as t prime times e to the kt plus kt times e to the kt equals 72k times e to the kt. At this point, we wanted to recall that the left-hand side could be written as an application of the product rule, where the product would always be our original function t times the integrating factor. Now, even though I've memorized this form, I think it's important that you verify that the derivative really does equal the original left-hand side. So let's apply the product rule real fast to this product. Recall the product rule says the derivative of the first, t prime, times the second, regular, plus by the product rule, the derivative of the second, the derivative of e to the kt is e to the kt times by the chain rule gives us this k times the first regular. And I'm not sure why I wrote that as a lowercase t right there. That should be e to the kt, capital T. Remember, I was just distributing this e into the parentheses. When you distributed the e to the kt into the parentheses, it's e to the kt times this kt. And that was a capital T right there. Okay. At this point, we choose to integrate each side of the dE with respect to t. Using the fact that the integral of the derivative will cancel since these are inverse operations. So we get t e to the kt on the left plus some constant of integration equals the right. Now on the right-hand side, we can tell that technically we require the u substitution method to find the integral of 72k e to the kt. However, I'm going to use the guess method. Because 72 and k are both constants, I'm going to look at just e to the kt and imagine that the antiderivative of e to the kt is just e to the kt. Now, if you were to take the derivative of e to the kt, it would be e to the kt times k, which is this k right here. So I'm going to say my antiderivative is just 72 e to the kt. Again, the derivative of 72 e to the kt is 72 e to the kt times by the chain rule, the derivative of kt, which is k, which gives us our previous line, plus some constant of integration. Now recall our discussion on these constants. Even though I wrote two constants, I probably should identify that they are different. However, I don't want to keep track of these two constants, how I manipulate them. So in future lines, I'm just going to combine these two constants and let it be some other constant c. So that we get t e to the kt equals 72 e to the kt plus c, where this c is really going to be c1 minus c2. Let's proceed to solve for t by dividing each side by e to the kt. And divided by e to the kt, we obtain t of t is going to be 72 plus c, and I'm going to introduce a negative exponent so I don't have to write this fraction. So I'm going to write a e to the negative kt. This is the general solution to this problem. Now there are two things we don't yet know in this problem still. We don't know what c is, and we don't know what k is. So let's go find these two constants. To find the first constant c, I'm going to use the fact that we know the temperature at time 0 is 450. We'll use this to find c. This other condition, t of 1 is 370, this one we use to find k. So at time 0, we know we have 450 is our temperature. So t of 0, of course, that's going to be 72 plus c e to the 0, and this has to equal 450. Of course, since e to the 0 is 1, this gives us that 72 plus c is 450. Of course, subtracting 72, we get c has to be 378. Which makes our model now look like t of t equals 72 plus 378 e to the negative kt. Now let's find k, using the fact that we know t after 1 minute is 370. So here t of 1 would be 72 plus 378. Now if t is 1, we get e to the negative 1 k. T is 1. Of course, I don't need to write that 1 there, but this has to equal 370. Okay, now let's solve for k. If we subtract 72 from both sides, well, 378 e to the negative k, and 370 minus 72 is 298. Now we'll divide each side by 378. And I'm going to write my decimal to 4 places. Of course, to be more accurate, you probably should just leave it as a fraction, 298 over 378. but I'm going to write it to 4 decimal places. 0.7883. Now to solve for k, we'll apply a natural log to both sides of our equation to get negative k equals natural log of 0.7883, or finally that k is equal to the negative of the natural log of 0.7883. Now this is pretty precise, but I want to write a decimal approximation just so we can use it in our work today. So I'm going to grab my calculator and do the negative natural log of 0.7883. And I think this comes out to be 0.2337. This makes our model look like T of t, the temperature at any time, is going to be 72 plus 378 E, remember the negative from our formula, negative 0.2337 T. This should be the equation that talks about the temperature of our object, the temperature of our pizza at any given time. Now, the question we were asking today was, how much time is going to be required for the pizza to cool to 110 degrees? So graphically, what we want to see is that if our pizza is going to cool down over time, this would be the temperature on the y-axis, and we know it's going to approach equilibrium eventually, which is going to be the temperature of the room. So let's put 72 degrees as our equilibrium temperature. Again, we know that we started at 450 degrees, which would be up here. And we know the pizza is going to cool down over time, something like this. So we're trying to ask in our question, when is it going to cool to 110? When will the pizza cool to 110 degrees? I probably should have spaced my graph a little further, but there's 110 kind of in the middle. So let's answer this question. We're going to have 72 plus 378 e to the negative 0.2337 t equals 110. And let's solve for t to find out when this equals 110. Now I'm going to do two things in my algebra here to save me some room. I'm going to subtract 72 from both sides and then divide by 378. So if you have 110 minus 72. That'll be 38. And then divide by 378. We should get e to the negative 0.2337t equals, and I'm going to write my decimal on the right-hand side to 4 places. So 0.1005. Of course, to be more accurate, maybe I should not do any rounding and just leave it as a fraction. We will now choose to apply a natural logarithm to both sides because the natural log and the exponential function e are inverses of each other. We'll divide by negative 0.2337 to get t is the natural log of 0.1005 divided by negative 0.2337. And if you're cautious, I think this should come out to be about 9.7 minutes. It'll take 9.7 minutes for our pizza to cool down for us to start to eat it. Okay, I hope this is helpful. Let's look at another example. Now, what I would like you to do is take a moment to read this example on your own. Pause the video, and then I'd like you to work at writing the differential equation. And just write the differential equation now. After that, unpause the video, and let's make sure we wrote the correct differential equation. And then we'll work on the solution after that. So please take a moment, pause the video, and write your differential equation. And the initial conditions that we're going to use to solve it. I'll see you in a moment. Okay, let's see how you did. So let's first write the DE, or I should just write the initial value problem because we're going to include the initial conditions. So let's write the IVP. Here we're going to have the temperature of the object, T prime, is equal to your proportionality constant K. Remember, it's always going to be the difference in your ambient temperature and the temperature of the object. Here they tell us a cold beer, initially 35 degrees, warms up to 40 degrees in 10 minutes while sitting in a room that has a temperature of 70. That is your ambient temperature M, the temperature of your room. So it'll be 70 minus T. For our initial condition, we know T of 0. Our can of beer started at 35 degrees Fahrenheit. And it warmed up to 40 degrees after 10 minutes. So T of 10 equals 40 degrees Fahrenheit. This is your initial value problem. Now, when we finally get to taking our exams, be cautious that in some of my questions, I ask you to not only solve the differential equation, I ask you to write the differential equation. Now let's look at the solution. In our last example, we found our solution using the integrating factor method. However, this time, I'm going to find our solution by the non-homogeneous principle. I could still use the integrating factor method. I just want to give you an alternative way for looking at solutions. Now, I should point out right now, and very emphatically, please, if nothing else is heard, hear this. In your textbook, there is a general solution to this differential equation. You should not use that solution that's already provided. Our class is not about memorizing solutions to complex differential equations and just plugging values in. I am going to be testing your method of solving a differential equation, not your method to look up a formula that's already provided. I will be emphatic on our exam. Show me how to find this solution using any algebraic method that we presented in our class. So be cautious that you don't use that solution form that's already provided. You must solve it by hand. Now, this time I'm going to use the non-homogeneous principle as our method. So here we go. To find our solution by the non-homogeneous principle, I'm going to again choose to rewrite our differential equation by distributing our factor k. And this should give us t prime 70k minus kt. And I'm going to get all of the t's on the left-hand side of the equation. So t prime plus kt equals 70k. And since we're using the non-homogeneous principle, I'm going to break our solution into two pieces. Let us first find the homogeneous solution. And then after that, we'll find the particular solution to the non-homogeneous equation. So we'll do these in pieces. Let's first look at the homogeneous solution. Now recall, for the homogeneous solution, we want the right-hand side to be 0. So we just make it 0, which gives us t prime plus kt is 0. And I'll move the kt to the right-hand side to get t prime equals negative kt. Now you can use the separation of variables technique to solve this differential equation. However, from form recognition, I recognize that there's only one function whose derivative is a negative multiple of itself. It has to be t homogeneous is c e to the negative kt. This is your homogeneous solution. Now let us find the particular solution to the non-homogeneous equation. Here we're looking at the entire dE, t prime, plus kt is 70k. And here, because the right-hand side is a constant, remember 70 and k is a constant, it's your thermoconductivity constant. Because the right-hand side is a constant, it makes me want to guess that Tp, your particular solution, is also a constant. So let's say it's a constant c. It's some constant. And if it's a constant, then we should be able to plug this constant back into the differential equation. So the derivative of some constant plus k times some constant has to equal 70k. Remember, if this is going to be a solution to the non-homogeneous equation, when you plug in that proposed solution, it better equal the right-hand side. Of course, since c is a constant, the derivative of any constant is 0. This gives us the equation Kc equals to 70k, and so we can see that c had to be 70. This is your particular solution. This is TP. So by the non-homogeneous principle, we can now say that the general solution has to be T of t is your particular solution plus your homogeneous solution. Now, in our solution, there are still two things we don't know. We still have to figure out what is our constant c and what is our constant k. So like before, we have two conditions that allow us to find these constants. We're going to use the fact that t of 0 is equal to 35. This is what we use to find our constant c. T of 10 is equal to 40. This is what we use to find k. Now, I'd like you to pause the video again because this is going to follow the same algebra we did on our previous example. And I'd like you to pause the video and go figure out what your constant c and your constant k are. Please do this, and I'll see you back here in a moment. Okay, I hope you paused the video and you already found your constant c and k, but let's do it together just to make sure we're doing the same things. We know at time 0, when you plug in 0, you're going to have 70 plus c e to the 0. And we know at time 0, our beer was at 35 degrees. This gives us 70 plus c is 35, which we should be able to obtain then that c has to be negative 35. This makes our model start to look like t of t is going to be 70 minus 35 e to the negative kt. Okay, now let's go find k. To find k, we know that after, what was it? It was after 10 minutes, it's at 40 degrees. So now we have t of 10 is equal to 70 minus 35 e. Now t is 10, which makes this be negative 10k. And we know this has to be equal to 40. So if we're solving now for k, you're probably going to be subtracting the 70 from both sides to get negative 35 e to the negative 10k. I think that's going to be negative 30. And then you're going to divide both sides by 35. to get e to the negative 10k, and you'll have 30 divided by 35. Now I'm going to write my answer here to 4 decimal places, but you might just want to leave it as a fraction to avoid rounding error. To 4 decimal places, you're going to get 0.8571. We'll then apply a natural log to both sides of our equation to get e to the negative 10k is equal, nope, I took a natural log. That e is not going to be there anymore. It's just going to be negative 10k is equal to the natural log of 0.8571. We'll divide by negative 10, so that k is going to be equal to the natural log of 0.8571 divided by negative 10. And if you're grabbing your calculator to confirm this, I think we should get k is approximately, if I go to 4 decimal places, 0.0133. So this now makes our model look like t of t as 70 minus 35 e to the negative 0.0133 t. This will be our model that describes how this can of beer warms up over time. So remember, graphically what we should be seeing here is that our equilibrium temperature was the room temperature, which we said was 70 degrees. And we're taking a beer that's starting out at 35 degrees, so down here. And we know over time this beer is going to warm up and approach the room temperature. It's not going to start to freeze, and it's not going to start to boil. It's definitely going to approach the room temperature. What we're being asked to find in this question is, when does it reach 52 degrees? So 52 degrees is about here. That's what we're asked to find. Actually, I think I missed part of the question now that I'm thinking about it. I think there were 2 questions here. What will be the temperature after 20 minutes? And when will it reach 52? So there were 2 questions here. So I'm going to do the 52 degrees portion first. So when will it reach 52? Okay, we're being asked to solve this question. So it would be 70 minus 35 e to the negative 0.0133 t, and we want to know when is it going to equal 52. Now I'm going to do 2 algebraic steps here at the same time. to save myself some room since I'm running out of room here. I'm going to subtract 70 from both sides and then divide by this negative 35. So 52 minus 70 is negative 18, and then I'll divide that by negative 35. So I'm going to get e to the negative 0.0133t is equal to I'm going to write my answer to 4 decimal places, 5143. I will then apply a natural log to both sides to get negative 0.0133t is the natural log of 0.5143. And then we'll divide to get t as the natural log of 0.5143 divided by negative 0.0133, which I think when you do on your calculator, you come out to be about 50 minutes. It'll take 50 minutes for this can of beer to warm up to 52 degrees. Okay, now the other part of this question was asking when will it read, or what will be the temperature after 20 minutes? So here we're just asking what happens after 20 minutes? What is T of 20? So when you evaluate T of 20, it's going to look like 70 minus 35 e to the negative 0.0133 times 20. And I think this should come out to 43.2 degrees Fahrenheit is your temperature after 20 minutes. Okay, so this should finish all of the examples I have in your guided lecture notes for Newton's law of cooling and Newton's law of heating. I'm going to stop this video here now, though, and I'm going to create a different set of videos to talk about the mixing problems. However, this should give you everything you need to know for the cooling and heating problems in your homework. I will see you in our next video for mixing problems.